similar to how human beings learn, how animals learn, by trial and error. So at every time, it takes an action and it observes a delayed feedback, and it only receives data related to its own actions. It is also a direct reinforcement learning is also a direct application of Markov decision process. That's why it has a good theoretical background. There are many real-world everyday applications of this reinforcement.
I'm sorry to interrupt. Do you mean to be changing your slides?
Is that?
We are only seeing your cover page at the moment.
Really? I'm sorry for that. Let me share it again.
Okay.
Okay, I'm sorry for that. I actually changed slides a lot. So yeah, maybe. Okay. So can you see all of the slides now?
Right, we can see your slides now.
Okay. So in machine learning, it is the timeline that I have mentioned. So it is starting from Alan Turing to invention of perceptron, then IBM's Deep Blue playing chess, and one of the last breakthroughs is the AlphaGo algorithm, which plays Go. And this is the categorization of this machine learning, which is supervised learning, unsupervised learning, and reinforcement learning, which is today's topic. Okay, I'm sorry for the inconvenience. Thank you for warning me. So yeah, in reinforcement learning, there is no supervisor, the feedback is delayed, there is some sequential data, non-IID data. So agent can only observe the outcome of its own action. So it is, and reinforcement learning also uses the framework of this Markov decision process. So, and it has many everyday applications, as I said earlier, from these autonomous vehicles to chatbots, and even Spotify uses this reinforcement learning algorithm to recommend some music for us, depending on our past listening experience. And even in financial, the stock market trading, they use reinforcement learning. So to use reinforcement learning, we formally define some main components. First of which is the agent, which is a part of the reinforcement learning, who actually takes actions and observes the results. Environment is that it represents the outside world. State is actually the condition that agent is in at any particular instance. Action is what the agent does, and the reward is the output. It's the feedback that the agent observes. So iteratively using all these components, a reinforcement learning algorithm learns. So one simple example of reinforcement learning is Q-learning, and it is also nice that it is theoretically proven that it converges to optimal policy. So Q-learning basically keeps track of a table which gives a value for each state and action values. So at any time, if I know this table and I know the current state that I'm in, I can choose the optimal action, right? So one simple example and a common example is this maze. Let's assume that an agent tries to find the treasure, but it also wants to avoid some enemies. So in Q-learning, we start by initializing these Q values. So it is basically the value of being at that state and taking that action A. And until the end of an episode or until infinity, it chooses an action based on its current estimate of these Q values, and then observes the reward and the next state. By using this observation at each step, it improves its estimates. Okay, so and iteratively it converges to the optimal Q values and then finds the optimal policy. When we talk about reinforcement learning, we always need to talk about this exploration and exploitation trade-off. So one thing that reinforcement learning agents can do mistakes is that if using the current estimate, if it always uses the best action that's based on its current knowledge, okay, it exploits the current knowledge, but it doesn't explore other actions. Maybe there are better actions. But if it explores constantly, then it knows the system very well, but it didn't take best actions. So we need to balance this exploration and exploitation in reinforcement learning. One simple example is this epsilon greedy. So at any time with some small probability epsilon, instead of taking the best action, I choose a random action just to explore the system. Okay, and a reinforcement learning algorithm can be considered in 3 types, which is value-based, policy-based, and actor-critic, which we will talk about later. A deep reinforcement learning algorithm is the most popular reinforcement learning algorithm. So remember that we have talked about this Q table, that every time we have a table showing the value of this Q function. So sometimes the states and actions are continuous valued, or they are very big, the state space is very big. So it is not feasible to hold this kind of a table. Instead, we use some neural network here. Neural networks are known to be universal approximators. So at any time, knowing just the state, we can approximate these Q values. So this is basically deep reinforcement learning powered by neural networks. So before going into detail this age of information, I'd like to talk to you about this 3-level communication problem, which is called as the father of all communication models and is developed by Ceran and Weaver. It organizes the communication problem into 3 levels. First level is level A. Is mostly dealing with how reliably I can transmit the symbols in a communication system. So this is what we always work on. It's like minimizing the delay, maximizing the throughput in a communication system, or minimizing the drop rate of packets. Level B, on the other hand, is related to this semantic problem. It asks the question about how meaningful my symbols. And the level C is the effectiveness problem. It asks the problem that how effectively does the received meaning affect the conduct? So how effective the result of my communication, and it depends on the application. Okay, so this semantic problem is very nice. People started to work on this, but it's rather abstract. What does it mean, the meaning? So age of information comes to help as a rather simplistic but an analytically traceable semantic performance metric. So it basically quantifies the freshness of status updates at any time, the timeliness of status updates at any time. So it can simply be defined as the time passed since the most recently delivered status update was generated. It has many applications, from smart vehicular networks to sensor networks to transmission of control signals, and it has shown to be very effective. So today we are going to talk about first a simple point-to-point communication channel. So we studied in our previous work that the sampling of a process of interest and the scheduling of this status updates over an error-prone imperfect channel. And we also assume a constraint on average number of transmissions so that we cannot transmit as we wanted. It can be due to energy or interference constraints. And we assume the real transmissions of the same packet, and we also assume the preemption of the transmission of a packet. For this, we study reinforcement learning methods. But before we are able to study these reinforcement learning methods, first we fit this problem into a Markov decision process. So the environment we talked about is basically the channel and gives us the probability of error. The state of our system is consisting of 2 components, first of which is the age of information at any time, and the second is the number of retransmissions. Number of retransmissions is important because we are using some error correcting protocols here. So if we keep retransmitting the same packet in an hierarchical protocol, for example, it can combine the information from previous transmissions so that it can increase the probability of success. So, and also the actions are defined. First of which is just simply to remain idle to save some resources. The second is the sample generate a new packet. and transmit it. And the third one is to retransmit a failed packet, which has a trade-off of transmitting a slightly older packet with higher age of information, but a higher success probability. And our reward is basically the minus age of information. Why minus? Because we are trying to maximize the reward in a reinforcement learning algorithm. We can also say that we try to minimize the cost, and we can define the top cost as the age of information. So, and this is the formal definition. We are trying to minimize the average age of information under a constraint on average number of transmissions. First problem arises here. Most of reinforcement learning algorithms are dealing with unconstrained problems. So first thing that we are going to do is to turn this problem into an unconstrained one by using a long-range multiplier method. So we are basically doing that. To cost, we have this age of information. We are adding some other costs related to the transmission. Okay, and we multiply it with a long-range multiplier. So this becomes an unconstrained problem now, and we can directly use a reinforcement learning algorithm. First, we investigate if an optimal algorithm exists for this problem and if there exists any structure of the optimal algorithm. And it does, luckily. So we can result that an optimal stationary policy exists, and it is actually a randomized policy, which is a mixture of two deterministic policies. And under some condition on this error correcting protocols, we can actually find a closed form threshold policy. Threshold policies are nice because they are computationally cost effective. But what if we do not know these system characteristics, these error probabilities? Then we use a reinforcement learning algorithm, which is called average cost SARSA with softmax exploration strategy. This average cost SARSA is very similar to the Q-learning that we have talked about previously. It is slightly different because it's an on policy, and instead of epsilon grid, here we use some softmax exploration. So at any time, we start with an initialization of this Q value, and then we observe the current state. So based on our current estimate of this Q value, here the state is age of information and the retransmission number and actions we have defined previously. And we do some exploration here. It basically does this. So the probability that I'm taking an action A at state Sn is proportional to its value, its state action value function. So, but after taking this action, I observe the next state and the instantaneous cost, which is the age of information, plus this cost related to the transmission. And then based on this observation, I update my estimate of this Q value. So I have the update parameter alpha here, which should be carefully chosen, but it is a topic of this stochastic approximation. I advise you to check if you are interested in this reinforcement learning algorithms. So this figure shows us the performance of our reinforcement learning algorithm, and the red line shows the performance of average cost SARSA. As you can see, it performs very close to the blue line, which assumes the system knowledge, which assumes the knowledge of these error probabilities. So after doing this nice example on this point-to-point case, now we need to extend our problem to multi-user case. So at any time, instead of deciding on whether to stay idle, sample a new packet, or retransmitting the previous packet, we also need to decide which user to transmit. So this problem has a very large state space compared to the previous one, and we can model it as a multi-armed bandit. Multi-armed bandit is a gambling machine, actually. So we are assuming that there are arms that we do not know its reward or cost distributions, and we try to find the best arm to choose, which means that we are trying to find the best user to choose at any time. So first, using this multi-armed banding theory, we are able to come up with a low complexity index, suboptimal but performing very well index policy. But this index policy assumes the knowledge of these error probabilities and system characteristics. So what if we do not know these system characteristics? Then reinforcement learning comes to help. Here we use more advanced reinforcement learning algorithms, first of which is average cost SARSA, which we used in the previous one with point-to-point case. The second one is average cost SARSA with linear function approximation, which improves the performance a little bit, but not enough. Then we use a more sophisticated one, which is deep Q network. And lastly, we have used this upper confidence reinforcement learning, which is based on this multi-empty bandit framework. So average cost SARSA with linear function approximation is nothing but for this kind of large state spaces. Instead of storing this Q table, we approximate this Q function with a linear function, like a linear function. And we choose these features ourselves, like this age of information or the retransmission number. But if its performance is not enough, then we need to use some non-linear approximator like neural networks. So in deep Q network, this is actually the algorithm that is used in AlphaGo. In deep Q network, we use a neural network, a deep neural network to approximate this Q value, so the value of state and action. And we also use different techniques, first of which is the experience replay. So if you remember that I told you in reinforcement learning, the data is non-IID, but these neural networks work better with IID data. That's why we use experience replay. So at any time we store some of our experiences in some replay memory. At any time, we randomly sample a mini batch and train our algorithm accordingly. The second technique is the two neural networks. So instead of one neural network, we use two, and which also improves the stability and robustness of our algorithm. And lastly, we use epsilon gradient. Although it's a simple exploration technique, it works very well in many contexts. And this table shows us some hyperparameters that we use in this DQM. And our last algorithm is upper confidence reinforcement learning. It uses some optimistic estimation of error probabilities, and it shows good theoretical performance. So in DQM, although it works very well, there's no proof that it is going to converge optimal value. But for this UCRR, yes, there's a theoretical proof that it converges to the optimal value. Although that it might be very complicated to run this. So this first graph shows us the average age of information per user with respect to the number of users in network. As we can see, our USRL2 algorithm works very well compared to our benchmark, round robin and greedy policy. So round robin is an algorithm which transmits to each user in turn, and greedy policy is an algorithm which transmits to the user with highest age of information. Second graph shows us how the average age of information for this DQN algorithm converges. As we can see, it learns how to transmit, how to schedule and sample in almost like 300 episodes for a 10-user network. Of course, as the network size increases, this number of episodes increases. And for a rather small network consisting of 2 users, we can compare all these algorithms. As we can see, average cost SARSA, the simplest case, okay, it tries to converge, but it doesn't perform very well. If we add this linear function approximation, it improves the performance, but not enough, although it's a fully online algorithm. And this UCRL2 and DQN performs much better than the rest. Okay, although that some of this average cost SARSA and average cost SARSA with linear function approximation doesn't work well compared to the other ones, they have one simple advantage is that they are simple. They do not require many computational power, and they are fully online. We do not need any pre-training. For example, for DQN, although it performs very well in many contexts, in many scenarios, it requires some pre-training and it requires some computational power. Sometimes it's significant. UCRL2 Vital works very well for this problem, but first, to use UCRL2, we need to show some structure on the policy space. So it is not useful always. After working on this multi-user case, we can also check the problem of minimizing average age of information in an energy harvesting context. In this context, in addition to unknown channel conditions, we also assume that we do not know the energy arrival process. So there are more unknown parameters. For this one, what we did was to compare this value-based and the policy-based reinforcement learning approaches. So value-based reinforcement learning approaches are helpful when we do not have many states, when we do not have many actions, and when we have discrete states and discrete actions. Policy-based approaches, on the other hand, is very useful when we have continuous state and actions. Also, if we can show some structure on the optimal policy, this policy-based approaches like this finite difference policy gradient is very helpful. For this one, with energy harvesting, we were able to show a threshold structure. So we exploited this threshold structure and offered a proposed an advanced and computationally efficient policy gradient algorithm. We also tried DQN for this one. DQN most of the time solves our problem, but as I said earlier, it requires some pre-training and it requires some computational power. So to parameterize and to approximate this threshold function, we use a sigmoid function. These sigmoid functions are universal approximators for this kind of threshold structures. And then doing some gradients on the policy space, we try to learn the parameters of the policy, which later corresponds to our actual threshold values. So threshold-based approach means whenever our age of information is larger than some value, some threshold, I choose to transmit. Okay, transmit to that user. And this graph shows us the comparison of this value-based and policy-based approaches. So as we can see from this graph, this GR learning is a value-based algorithm. And the purple one and the blue one here, they are the policy-based algorithm. As we can see from the graph, the policy-based algorithms converges much faster to the optimal value shown by this blue line, RVI. They converge much faster than the value-based. Why? Because they exploit the structure of this threshold. Value-based approaches, on the other hand, uses this Q-learning kind of thing. It is a general algorithm. Although it performs okay, but it doesn't get close to the ones with the policy gradient. And the second figure shows us the performance with respect to this correlation coefficient in the energy harvesting. So in this work, we modeled this energy harvesting as a Markovian process. So as it gets more temporal coefficients correlated, the average age of information increases. So up to now, I tried to show you, summarize you an example to reinforcement learning approaches to average age of information problem. So what is next? What we can do? There are actually many use cases of machine learning for the 6G and beyond, increasing this ultra reliable low latency network, increasing this edge artificial intelligence, and we are currently working on this. Second one is this communication for federated learning. So this, up to now, we have discussed these learning algorithms for communication problem, but it can be other way too. So we can also use communication techniques for machine learning algorithms. As machine learning algorithms get more and more distributed, they are mostly communicating over a wireless channel. So this noise, these errors, and this algorithms on how to communicate the information between them is becoming a bottleneck. So also the slowness of this gradient updates, for example, for a federated learning setting where distributed servers are cooperating to learn is very important. So slowness means the age of information. So we can also use age of information as a performance metric for a federated learning, for a distributed learning system, which also corresponds to the effectiveness problem, which is level C in Shannon-Weaver model. Another use case is a multi-agent reinforcement learning. So sometimes these reinforcement learning algorithms are also distributed. So multiple agents are communicating to achieve a common goal or to achieve their own goals. So, but they are communicating over a channel, a wireless channel with noise and with packet drops as well. So we can also try to find ways to communicate efficiently, effectively, so that this multi-agent reinforcement learning algorithms works well. So this is the end of my presentation. Thank you very much for listening. I hope I have finished in time. If you have any questions, it will be my pleasure to answer them.
Thanks a lot, Elif, for this very interesting, very timely talk. Are there any questions from the audience?
It was a little bit fast. I'm sorry for that. I tried to cover as much as I can.
Any questions? Well, I have some questions. Maybe we can start with my questions. Toward the end, I was very intrigued when you said the federated learning problem is related to the effectiveness problem in Weaver's designation of the 3 levels. Could you expand on that, because that was kind of fast?
Yeah. So effectiveness is related to like how our communication is effective at the end. So because we are communicating, we are trying to send the symbols. But at the end, if we know the use case, if we know that how useful our information for the end goal, we can design our communication algorithm accordingly. For this federated learning example, for example, let's say that I'm trying to train a machine learning algorithm which does a classification on images, like cats and dogs images. So if I know that how this distributed federated learning, the performance of distributed and learning changes with respect to my communication algorithm, I can design my communication algorithm accordingly so that I can address this effective communication level. Is that clear, or shall I?
So, as opposed to age of information, for example, you classified age of information as level B, the semantic problem, whereas this is level C. So here there is some additional information that we're using from the destination, right? I mean, in age of information, maybe the information is coming only, the feedback is coming from the receiver, whether the packet has been received or not. But here, I think you mean whether the learning has been successful. The feedback is related to the application itself. Is that how?
Yeah, the feedback can be related to convergence speed, for example. I want to converge as much as I want. So if I can see a relation between this age of information, this slowness, and the convergence speed, if I can model it, then I can address this effectiveness problem.
So if you just model it once and then use its estimated value, or do you really obtain actual results on the convergence?
For start, we can do like modeling it once, but it is an abstract, it would be an abstract model. the most useful thing to do is to learn it during this convergence, learning during this training.
Mm-hmm. Nice. Because can you relate this to the value of information concept in control? In control, they have VOI, as you know.
Yeah.
That's also in this group of effectiveness.
Actually, it can be. I was considering on that, but it's again a model. I don't know. I don't think that they show the actual effect on the control problem, right? It is again a model.
Once, I think.
Yeah. It can be considered as effectiveness, but usually the effectiveness is like this, showing this convergence speed. For example, in a noisy channel, in a physical layer, if I choose like my codes according to, while training a neural network, for example, if I put also noise to that training, then it means that I'm training considering this wireless channel as well. So usually we are trying to look at the actual performance in this effectiveness problem. Mm-hmm. But I think the value of information is a good start from semantics to effectiveness.
Thank you so much. That was very enlightening for me. Yeah, any other questions? Looks like
thank you.
Other questions at this point. We thank the speaker.
Thank
everybody for attending. And enjoy the rest of your week. Bye-bye.
Thank you. Bye-bye.